talking about the Schmidt process. So in order for us to go through this content, I'll have to assume that you know the basics of vectors. So what vectors represent, with the magnitude, direction, doing like basic vector addition, subtraction, all those things. But otherwise, what I talk about in today's video, you should be able to figure out relatively easily, hopefully. So with the Schmidt process, what we want to do is, if we have two vectors, right? So two vectors A and B, and if the two vectors span the whatever vector space you're working in. So in this case, we have a 2D graph, right? So we have two dimensions, and if the vectors span the full space, then we want to find, and if they're linearly independent. So that just means we have a basis, right? We have a basis for vectors, right? So we have two vectors, and we're working in 2D space. So you want the number of vectors and the number of dimensions, quote unquote dimensions, to match, right? To put it very simply. So when we do have a basis, right? So we have a basis A and B, and we know that they span the full vector space, right? So you can call it R2, or you can call it the Cartesian plane, or the 2D plane. Right? But just to show like a visualization, right? The vectors spanning the space just means that we're able to access every single point only using vector A and vector B, so vector addition and scalar multiplication. Right, so we're able to access every single point on this graph using vector A and vector B. And just by looking at these grid lines, I haven't shown all the grid lines, but we can see that we're able to access all the points using scaled versions of the vector or adding the vectors together. So now, once we have a basis, right, a vector, once we have a basis that spans the vector space, what we want to do is find the orthogonal basis of the vector space. So how do we do that, right? Like, when we think about it, it seems kind of tricky, but then one thing we could try is to find which components of the vector are the most essential. So what I mean by that is, if part of a vector can describe another part of a vector, that means that there's kind of like unnecessary information, right? So to say, not necessarily, but there's a bit of unnecessary information, right? So for this example, let's say for vector B, for example, right, for vector B, we if we let's just say assume, right, just to take one vector as an example, we can see that vector A, some component of vector A is described by vector B, right? If we draw kind of like a dotted line down, vector A has two components, right? It has this component, right? It's got this component that's described by B, right? So this part, we can call A described. So I'll write DES, right? Described by B. Whereas the other side, right? The other side, it's not described by B, right? It's orthogonal to B, right? To be more specific, right? Perpendicular to B, right? So this is A, let's say not, right? Not described by B. So basically what this kind of visualizes, what this kind of gives us is an idea of how to construct orthogonal bases, right? Orthogonal in the sense that there's a more formal technical definition using inner products, but like an intuitive definition would just be, right, it's perpendicular, right? The vectors are perpendicular to each other, or they don't have any components with each other. And one way to figure that out, right, is to use the projection, right? So I wrote this down already. This just means, let me circle it. But the symbol, right, this symbol just means perpendicular. This symbol just means parallel. And so now we actually want to find the projection of B onto A, right? So we're doing the opposite of what we did initially. And we can figure that out. There is a formula for it. It's actually just, if we want to find the projection of B onto A, right? So if we want to find the projection of B onto A, then what we actually want to do is find the dot product. The dot product of B dot A, and then divide it by the dot product of A dot A, and then multiply this whole thing by the vector A itself, right? So just vector A itself. If we want to find the projection of B onto A, right? So this component right here, this vector, let me draw it in purple. But if we want to find this purple component of B right here, then this would be the formula we would use. And the formula makes sense, right? If we kind of go through it step by step, basically what it's saying, right, with the dot product, it's telling us we want to dot B with A, so whatever component B has in similarity with A, right? So this component right here, this purple component, we want to multiply it by A itself, right? So it's going to be some vector. It's going to go a lot further, right? It's going to be a dot product, but it's going to be something like that. But it's in the same direction, right? And then A dot A would give us the same vector. Let me draw it in green, but instead, right, it would just be A itself, right? A itself dotted by A. So it would be the same exact vector, or the same. It would have the same direction as B dot A, right? The vector would have the same exact direction. And by dotting it, you're basically just finding a ratio between B and A, right? The component of B. So this purple, the purple vector B, the component of B, and the blue vector, right, which is A itself, right? So you're kind of finding the ratio between the two, right? Because you're both dotting by the same exact value. But because you're dotting by the same exact vector, you're just finding basically the ratio between A and B, or B and A, right? B divided by A. And once you find the ratio, and you multiply it by A itself, right? Then you get the magnitude, right? The ratio times the actual magnitude and direction of B projected onto A. And so, this gives us a very neat and nice formula to figure out how to kind of like subtract out components that are kind of unnecessary, right? Kind of unnecessary. So now, what we can do is we can go into the full Gram-Schmidt process, but basically, what we'll be doing is, see if I can. So we're starting with vector A, right? We want to start with vector A. You can start with any vector. So you can start with vector B if you wanted to. We're just starting with vector A in this example. So we take vector A to be the first orthogonal vector, the orthogonal basis vector. And then once we do that, next we want to find the second orthogonal basis, right? We want to find the second orthogonal basis. And we do that by using the second vector B, right? The second vector that spans the space B. But we know that B has two components, right? It's got this component, right? This yellow component already described by A. But then it's also got this purple component, right? This purple component vector C that's not described by A. So what we're doing is we split B, right? We split B into its two components, right? Let's call this D, right? Vector D, right? So B is equal to, we'll have to flip the directions, but B is equal to D and C, right? The components of D and C. Let me flip that right now. Right, D and C. There we go. So B is equal to D plus C, right? And that's just from basic vector addition. And then what we can do is we can just subtract out this D component, right? The D component that's already described by A, right? It's in the same exact direction as A. So we're all we're left with is C, right? Which is orthogonal, right? It's perpendicular to A. So if we just use the formula that we kind of intuitively found out earlier, right? So let's call the orthogonal basis like vector O, right? O1, or let's say R. It doesn't really matter what we name it. O is a little bit, it looks like 0, so we'll call it R. So the orthogonal vectors we'll call R1 and R2. And if you have higher dimensions, right, it's going to be R3, R4, etc. So first, right, R1 is going to be equal to A, right? We just set R1 equal to A because we need to start somewhere. And then with R2, right, if we want to find the orthogonal vector R2, all we have to do is, so we take vector B, right, the second vector of our vector space, the second vector that spans our vector space, and we just subtract the projection, right, the projection, whatever's parallel to A, right, whatever in B, right, projection of B onto A, right, whatever is parallel to A. Right, and then we know that formula, right, from earlier. That's going to be B minus, it would be B, let me just double check just to make sure I don't get this wrong. Yes, okay. So it would be B minus B dot R1, right, which is equal to A, right? R1, which is equal to A, and divided by B dot B, right, times B. And this whole thing, let me circle it in yellow. This whole thing in yellow, right, B dot R1 divided by B dot B times the vector B itself, right? That is the projection, right? The projection of B onto A, or R1, right? A is equal to R1. And then once you get that, R2 is equal to C, right? So what we highlighted as C, that is R2. And then for higher dimensions, you just repeat this process. You've got you found the two orthogonal bases, right? And then so for the third one, you just want to subtract, so you take the third vector that spans the space and then subtract all the projections, right? All the projections onto it. So you're left with only one component that's perpendicular to everything else, right? You want it to be perpendicular to A and B. So you just basically repeat this process over and over, and that's pretty much the Graham-Schmidt process. The last thing left to do, and this might make solving some some systems of equations easier, is if you put it into orthonormal. Orthonormal, and that's just you normalize all the vectors. You normalize all the orthogonal vectors, right? So we have R1, R2. So all you're doing is, we can call it N for normal, right? N1, N2. All we're doing is we're dividing it by the length itself, right? So we make it a unit vector, right? The magnitude of the vector becomes 1. So N1 is going to be equal to R1, so the vector itself, divided by the magnitude, right? The magnitude of the vector. Technically the L2 norm, so it's just the magnitude. And the magnitude is equal to the square root, right? Square root of x squared plus y squared plus z squared. So all the components squared. So it's like the Pythagorean theorem, basically. And you can repeat this for higher dimensions, right? You can repeat this for higher dimensions. And the cool thing about orthonormal, right? So the cool thing about orthonormal vectors is it actually, if you take, I'll call the orthonormal matrix N. Right? So this is actually, let me specify it, right? So this is the matrix N, right? Not the vector N, the matrix, right? And N equals all the vectors, right? So the vector N1, vector N2, N3, and so on. In this case, we only have 2 dimensions, right? But N1, N2, dot, dot, dot. If you have the matrix N, if you multiply it by its transpose, so that's just flipping it across its diagonal, right? So if you flip it across its diagonal, multiply it, then you'll end up with the identity matrix. And that'll be true, right? Whichever way you multiply it, right? So if you multiply the transpose by the regular orthonormal matrix, you'll also get the same thing, and that makes sense, right? Since all the vectors are orthogonal to each other, right? All the vectors are orthogonal to each other. If you multiply an orthogonal vector by itself, by another orthogonal vector, right, you're going to get 0. Right? The dot product of 2 perpendicular vectors, right, that's 0. And dot product of 2 parallel vectors is the vector squared, right? So you're getting vectors squared, right? And you're adding them all together. And since, by definition, right, we made the orthonormal vector the magnitude 1, that means that we're adding all the components together, right? All the components squared together, which means we're going to end up with 1, right? That means we're going to end up with this diagonal matrix, right? The identity matrix, to be more specific, right? So we're just going to end up with this, right? With 1s on the diagonal like this. And it's a very cool, very neat, and pretty intuitive way of constructing orthogonal vectors, right? The Graham-Schmidt process is pretty darn cool. And it can actually be used for things also like they can be used for QR decomposition, which I might talk about next and why it's useful. It has to do with like a numerical stability and things of that nature. So it comes down to having like fixed points, having well-behaved linear functions. So it gets a little bit more technical, but for this video I just wanted to talk about the Graham-Schmidt process, and hopefully these visuals kind of helped make the process more intuitive. I hope you enjoy the video, and please let me know if you have any questions in the comments below.